importance of models and why that matters. I'll discuss then the concept of half-light radius, which is important for the actual measurement of galaxies, discussing how it relates to galaxy morphology, where we get information about light apertures and their flux through galaxies, and how I make measurements in my code. Lastly, I'll discuss the heuristic index and the effectiveness of my code in the actual. So, this is unfortunately actually not how it went, all things considered, but when you do work like this, and as an astronomer, there is so much hidden information when you look at objects in the sky. Most of them are big white dots. So when you look at something, there's a lot of stuff hidden that you need to either infer or use models to develop and get understandings from. So what was I trying to confirm? Well, I was trying to confirm that with the new JWST telescope, our current existing models for galaxy formation and surface brightnesses still function for them in their high redshift universe. So what are good models, right? We analyze astronomical bodies for many reasons. So how do we do it, right? Well, we need good models that are based on reliable observations. They can explain the characteristics of our observations. Most importantly, they are predictive, meaning that we can extrapolate from the data we have of our model to find unknown objects so far that we can, so if we find them, we expected them. And they're able to predict new phenomena or explain new phenomena when we find something that we hadn't predicted in our measurements, so that they will still fall within the model. So now that we understand what makes a good model, let's move on to how astronomers use model galaxies and the half-light radius. So this is the first component of galactic analysis I was working on in determining, through my code. So very simply, the half-light radius is a tool that astronomers use to gauge the rough size of galaxies. Because unfortunately, galaxies don't have walls, really. But literally just the radius at which half of the light of the galaxy is contained. This generally means that with half the light contained, it's going to be most of the mass contained. So we can roughly approximate how big it is and where it sits. But how does this relate to other galaxies and other different kinds of galaxies? So this brings us to galaxy morphology. Now, what does morphology mean? What are we talking about here? All morphology really means is the size and shape of galaxies. Now, for my project, I was working primarily with spiral and elliptical galaxies. And they've got different shapes. They're different. They look different. So they're going to behave different. With a spiral galaxy, it's all big and spread out. And it's actually rather evenly distributed. But with elliptical galaxies, they're really concentrated. They're very centralized. So how do we measure these things? Where do we take this and get it and put it into data? Well, we do that by looking at luminosity, fluxes, and apertures. So very simply, luminosity is just the amount of light emitted by an object. A 100-watt light bulb will emit roughly 100 watts of light. Then to calculate flux, we actually need to talk about aperture real quick. So aperture is just the largest dimensions of the light collecting area of whatever instrument we're talking about. So if it's a lens-based telescope, it's how big that outside lens is. If it's the JWST, then it's the size of the mirror array that it uses to collect light. And lastly, flux is just the count of how much of that luminosity passes through the aperture. So that allows us to gain understanding of how much light we're actually receiving. So now that we understand what flux and apertures are, let's put them together and see how I use them and what they can tell us. So this is about what I did. This is an approximate model of how my code works. I would take an aperture centered around 0 in the center of the picture and expand it over time procedurally over the image. That right there was the model galaxy I worked with. Much like all things in astronomy, it's a white blob. So this is how this is what my code did and how it measured my data. So let's look at the actual data itself. and what I got out of it. So again, expanding this aperture over time. This isn't the actual aperture, I did that in code. So here we have some very pretty 3-line graphs. But we can actually take a lot of information from this. So this, the important thing to note first is that y-axis there, the flux through the aperture, is inverted. So the 0 is actually at the top. There's a reason for this. This gives us the form of a characteristic shape of a graph that is related to that Sursic index model that I talked about earlier, and I'll get to again in a bit. Now you can see here at the bottom that this black line is approximately where all the light kind of evens out, the total average of all that light once the entire galaxy is modeled. Now, this can depend on how you measure it, but since my code normalized everything to 1, the total count of light was 1. So what I was able to get was this half-light radius, this point in between where half the light is encaptured, and that's at 0.5. And I'll get to how I use that in a bit. So let's talk about that characteristic growth curve, that light profile of a galaxy. So this is the Sursic model. Or more accurately, it's a representation of what we can do with the Sursic model. It's based on these n values, these index numbers. They are used as an exponent to model the size and light profile of galaxies. Now, while we've got these all different types of very extremized shapes, all the way up to n10, which is very extreme, and down here this n.5, there really aren't anything beyond n1 and n4. These are just a model demonstration of how we can take the model. So when we take a look at n1, for example, we've got this very long straight line. That is actually a representation of how, over the radius distance and the brightness of the galaxy is very distributed, which represents a spiral galaxy. And if you take something up to the n4, this red line here, this very extremized line, which matches similarly to what I had in my code, you see it's at a very condensed, centralized point, and that represents more of a elliptical galaxy. Oh God. Don't worry, it's not that scary. There's a lot of terms here. So this is the Sursic model itself. The surface brightness is where we calculate, and that's that whole curve over time. But then there's a bunch of other scaling factors and effective brightnesses, the radius from centers and the defective radius from earlier, the half-light radius. And then here, what the most important part, that Sursic index. And you can see how this 1 over n factor of an exponent actually gives us that characteristic curve of that L shape. So let's bring it back to the galaxy morphology. So as you can see, n equals 1 for the spiral galaxies, and n equals 4 for these elliptical galaxies. All right, so with all of this in mind, with all the way I've been able to generate a shape of the galaxy that's proper and correct and matches my expectations, what have I actually managed to figure out? Well, with my galaxy, I was able to determine by taking that intersect point of that 0.5 on the graph and drawing a straight line down, I determined that the half-light radius in pixel measurements of my galaxy is 6, which, yeah, there's a lot of pixels in this, and it's all right there, real tiny on that big blob. Now, I also knew for the fact about this image of mine that it had an arc cycles, a 3.031 arc seconds per pixel conversion factor, and that's just to relate it to the model's shape, because this was a generated model, so it isn't actual telescope data or anything. And that allowed me to actually take this to be a 0.186 arc second half-light radius, which is a more standard astronomical measurement tool, measurement unit for the dimensions of things in the sky. This also was approximately correct for the generating factor, the half-width maximum of the point spread function that was used to generate that initial model galaxy. So I was able to determine that my model can correctly analyze the galaxies that I'm fed and properly output both the galactic curves and properly reference the half-light radiuses. I'd like to thank the Physics and Astronomy Department oh so very much for dealing with me for these past 4 years and for the great education they've given me. Special thanks to Dr. Thomas Target and Pedro Jesus for all their guidance and collaboration. And I'd like to thank my parents for the support their entire time.
All right, any questions for Erasmus?
Well, you mentioned that you recovered it. There was an input model to generate it. It was kind of I don't know if it was presented to you as a challenge or a quest to, can you develop the code that gets this and measures this accurately, but do you have a kind of a percentage of how close you got to the official model?
Yeah, in a sense, that actual half-width maximum that was used to generate the point spread function that I analyzed was 0.150. So compared to my 0.186, it is different, yes, but that's close enough for government work for now.
Plus or minus.
Yeah, plus or minus a few. So.
All right, any other final questions? If not, let's thank Erasmus.